Ik ben Dave Aronson, de T-Rex van Codosaurus. En ik ben hier heel gevlogen op mijn pterodactylus om jullie iets over genetische algoritme te leren. Maar ik zal het in het Engels doen. Mainly because you've just heard almost all the Dutch I speak. So what are genetic algorithms in the first place? The whole concept is a set of optimization meta-heuristics, which is fancy talk for a category of shortcuts for finding solutions to a problem, ideally the best solution, but we usually have to settle for something good enough due to constraints like time and money. There are many kinds of optimization meta-heuristics, but genetic algorithms in particular are unique in that they are inspired by real-world biological evolution. In particular, the principles of survival of the fittest, random combination of old sets of genes, no, not like these, into new ones, and random mutations. The history goes back to about 1950, when Alan Turing, as in Turing completeness, Turing machine, and the Turing test mentioned right on this stage this morning, proposed a learning machine in which the mechanism of learning he thought would be similar to evolution. Nothing much ever came from that, nor of genetic algorithms in general for the next few decades. But finally, the first genetic algorithm commercial product came out in the late 1980s, a toolkit for industrial processes to be run on mainframes from General Electric. These days, most major programming languages have one or more little libraries that you can use for genetic algorithms, and similar tools are built into things like MATLAB and so forth. But the actual uses of genetic algorithms remain mostly rather obscure, used by companies internally for their industrial processes, logistics, scheduling, and so forth. But once in a while, they do get used for something a little more interesting and more publicly known. Most famously, in 2005, NASA used a genetic algorithm to design an antenna for its ST5 series of spacecraft. And no, that's not just a bent-up paperclip. The NASA Jet Propulsion Laboratory website says its unusual shape is expected because most human antenna designers would never think of such a design. And that is actually one of the great strengths of this approach. So how do genetic algorithms work? Most developers hear the name and think, oh, that must be horrendously complex. But they actually consist of a fairly simple series of steps. First, we create an initial population of candidates. And in genetic algorithm terms, these are usually called chromosomes. But since practically every living being contains lots and lots of chromosomes in every cell, I think that term is misleading. It just leads to confusion. So I prefer to just call them candidates. There are several other names you can call them. The next step is to assess how fit each of these candidates are for our purposes, according to whatever criteria we wish to apply. Then we can ask, are we done yet? This is usually based on the fitness, which is why we just figured it out before this step, or it can be based on other criteria or a combination. If we're not done yet, then next we select some breeders to use in breeding the next generation, then of course actually do so. Next is a very important but unusual step, and that is to mutate these new candidates for more diversity in the gene pool. Then we go back to step 2 and ask how fit these candidates are and begin a new cycle. This could be represented at a rather high level in code like this. This happens to be in Ruby. I chose that not only because it's the one I'm most familiar with, but it reads closest to plain human language. So even those of you who've never done Ruby, I figure you can probably understand that. Now let's look a little closer by working through some examples. First, we create our initial population of candidates. But what is a candidate and how do we create one? These are different solutions to some particular problem, and they can be represented by any data structure we want, so long as we can evaluate how fit they are for our purposes, combine two, or sometimes more, into a new one, and mutate them somehow. The simplest common type of candidate is a simple string of bits, and this will do fine for candidates that consist of a simple series of yes and no decisions, such as for knapsack-type problems. To look at a specific example, suppose we know a farmer with a fairly smallish truck, and he needs to decide what to take to market once a week. And on this farm, he has some cows, E-I-E-I-O. So among the things he can take to market are cows, milk, cheese, butter, ice cream, meat, and leather. His truck has room to take everything, but it can only take so much weight, so that's going to be our constraint. His choices are as follows, with some simplifications. You don't need to remember anywhere near all of that, just notice that it totals 8,600 pounds. However, his truck's suspension can only handle 4,000 pounds. So let's use a genetic algorithm to determine a good enough truckload that fits within that constraint. And first we need a way to represent each candidate. In code, we could use a class like this. Oh, that looks like we're just making a random number. That's right, we're making a random number with 7 bits. So we have a random 1 or 0 for each of these 7 things that we could possibly take. And we could get as complex as we want in this function, like having a minimum or maximum number of items, but let's keep it simple. To create an initial population, as opposed to just an individual, we could create a bunch of candidates and stuff them into an array like so. And this could be done with much more idiomatic Ruby, so those who do know Ruby, please don't scold me for that. I'm just trying to keep it understandable. So if we create an initial population of 10 truckloads, that might look something like this. And for now, I'm going to just hand wave over how we decode those random numbers into these combinations of goods. However, the last slide of this presentation contains the URL for the GitHub repo where you can see all the gory details in the code. Next, we assess how fit each of these are, and we do that with what's called a fitness function. Surprise! And just like how biological creatures might be perfectly fit for one niche, but a horrible fit for another, this needs to reflect how fit these are for our purposes. In this case, we know we want the just plain raw cash value, and we're going to, again, hand wave over the difference between price and profit and so forth. However, any truckload that is too heavy for the truck is absolutely worthless because we just can't do it. So in Ruby, that filtering would look like this. We cycle through the item numbers, summing up the weights. If that exceeds the capacity of the truck, we return 0. Otherwise, we, again, cycle through the items, summing up the values of the ones we want to take. Again, we could get as complex as we want in this function, and NASA's antenna fitness function certainly must have been. For instance, if the truck were smaller, we could also take into account the volume of each item. Anyway, if we run this function on our current population, we get this. Now that we've assessed how fit each one is, we can ask, are we done yet? but what are our criteria? This function can be very simple, but it can take a lot of thinking to figure out exactly what it should do. With an APSAC problem, a good solution, or even the very best solution, can be made utterly worthless by adding one more item and thus exceeding the capacity. So what we're going to do is hang on to the best one we've seen so far and just try to outdo it. We're done if we haven't seen anything better in 100 generations. And in Ruby, that would look like this. And I'm going to hand wave over explaining that code. Again, we can get as complex as we want with things like not just checking the fitness, but also things like a maximum total amount of time, whether watch time or CPU time or number of generations maximum, or we could rig up some way to let the user press a stop button or use a combination of any of those. Since we've just created our initial population, we're obviously not done yet, so the next step is to select some breeders to breed the next generation. And the obvious way to do that is to take the top two most fit, like so. Out of our current population, that would choose these two. And as usual, we could get much more complex if we wanted. For instance, there is a technique called roulette wheel selection. Now, you would think roulette wheel would have identical size slices, but no, in roulette wheel selection, each one has a chance to be selected proportional to its fitness. So you do get some influence for survival of the fittest that way. Now that we have chosen our breeders, next we actually breed them. And the usual way to do this is called crossover. That consists of taking the data points, or in genetic algorithm terms, the genes, and hence the name, from the first parent up to some randomly chosen crossover point, after which you take them from the second parent. And this can be extended with multiple crossover points and so forth. You can even have 3 or more parents, but we're just going to keep it simple. 2 parents, 1 crossover point, like so. We establish the crossover point as a random number between 0 and however many items we have, and go through the items. If we haven't hit the crossover point yet, we get it from the first parent, else we get it from the second parent. With a random crossover point of 3, that would get us a new combination like this. But this is just one of 10 results because we're creating a whole new population. And we can do that like this. Notice that this is almost exactly like how we created the initial population. But instead of each candidate being constructed from scratch, now it's the result of breeding our 2 breeders. That's the only difference. The whole list for the new population might look like this. Notice we have lots of family resemblance. None of these loads contain a cow, or butter, or leather, or no cheese. That's because both of our initial breeders were like that. If we were to just continue breeding the best of every generation, we'd never see a truckload containing a cow, butter, leather, or no cheese. But we fix that in the next step, which is to mutate them. Again, I'm going to keep it very simple and just give each gene a 1 in 4 chance of flipping. And in code, that would look like this. We iterate through the item numbers, and if a random number from 0 to 4 is a 0, then we flip that down. Again, we could get as complicated as we want in this function, like having some genes more likely to mutate than others, or having a minimum or maximum number of mutations, or all kinds of other complications, but I'm going to keep it simple. If we run this mutation function on our current population, we might end up with something like this, where the green color means it changed. And you can see that we now do have some truckloads that include a cow, butter, or leather, or no cheese. Now we go back to assessing how fit each of these are, which we couldn't do until we mutated them because the mutation would change their actual fitness numbers. And if we, whoa, what happened there? Okay, I guess that screen times out or something. Sorry about that. I'll try and remember to flip over there once in a while. Anyway, if we sort on fitness descending, we get this. That just makes it easier to find which ones are the best. But you can see that our maximum fitness actually went down from 20,000 to 15,000. But that's all right. As you may remember, we just hang on to the old one and try to outdo it. So we haven't lost it. It's okay. The next generation might look like this, a small improvement on our previous best one. So we set that top one as our new best combination and reset the counter of generations since we've seen it. If we let this run to completion, we might wind up with something like this, with our best truckload scoring 26,000, made up of cheese, meat, and leather. So that's one complete run of a genetic algorithm. If we thought, oh, maybe this can do better, we could just run it again and again and again, as many times as we like within reason, since, at least in a real-world case, it's probably much more efficient and effective to write this code and run it rather than brute force our way through the entire solution space, or in some cases, precise calculation. For this particular thing, 7 choices, 1 truckload a week, no big deal. But if we had dozens of choices, much more complex criteria, and many truckloads per day, yes, it would be well worth it to have a genetic algorithm determine our truckload contents. Now, suppose we want to evolve something completely different. Suppose we want to evolve a good set of character stats for a Dungeons & Dragons fighter character. D&D character stats are strength, intelligence, dexterity, constitution, wisdom, and charisma, each determined by rolling 3 6-sided dice, or 3d6 as we said back in the day. Though I'll hand wave over how you can sometimes have extra strength. We'll just ignore that completely. In Ruby, that might look like this, though the roll function is left as an exercise. Should be pretty simple. So if we create an initial population of 10 characters, it might look like this. Then we assess how fit each one is. And since we're trying to evolve fighter characters, there goes that screen again. Okay. It should be based mainly on the strength and constitution. The dexterity also helps, but the other things, not so much. But we still don't want them too low for the sake of occasional saving throws. I tried several different things, such as totaling up twice the strength and the constitution and half the dexterity, but the other stats tended to get too low, and even the dexterity wasn't very good. So I tried prioritizing them linearly, adding up 6 times the strength, 5 times the constitution, and so on down to 1 times the charisma. But the other stats then got too high, and the characters were too generalized. So I finally settled on prioritizing them much more strongly in a geometric progression, totaling up 32 times the strength, 16 times the constitution, and so on down to 1 times the charisma. And that yielded pretty good results. But the point of that part is it can be very difficult to figure out what the fitness function should do to yield the results you want. The other possibilities yielded perfectly good fighter characters, but not very good as D&D characters overall. Wanted a little better mix there. Anyway, if we run this on our current population, we get this. And now that we've assessed their fitness, we can ask, are we done? But what are our criteria? Let's say we consider it done if any character gets 90% of the way to the maximum fitness score of our fitness function. And I'll spare you the math, but that works out to 1,021. In code, checking that would look like this. Very simple. None of our candidates in the current population score anywhere near 1,021, so we select a couple breeders, and I'm going to stick with the tactic of picking the top two, which would get us these two. And then we actually breed them. But this time I'm going to use a slightly different approach, not the crossover, but essentially flipping a coin for each gene, like so. We flip a coin, or in this context, roll a D2, and if it comes up a 1, we get that stat from the first parent, else we get it from the second parent. And that could get us a result like this, with the coloring showing which parent it came from. And again, this is just one out of a whole population of 10, which might look like this. And there are two things to notice here. First, the count of red and green are not always the same. In fact, they're fairly rarely the same, either within an individual or the entire population. But there's, again, a lot of family resemblance. For each stat, there are only two possible values, or in genetic algorithms terms, alleles, even though we supposedly have the whole range from 3 to 18. There's only two values because, of course, they had to come from the breeders we used. If any of the stats were the same between the two breeders, there would be only one possible value in a given column and half as many possible combinations. Now, at a glance, you can tell from the important stats that these are a little more suitable as fighters than our previous generation, but we'll figure their actual fitness scores later. And again, if we were going to continue breeding the best of these generations, there would not be any change in the possible stats in the alleles of each gene, or the possible values of each column. But we fix that in the next step, which is to mutate them. And again, I'm going to keep it very simple. I'm going to give each gene an equal chance, 1/3 chance of staying the same or going up a point or going down a point, within the valid range, of course. And in code, that could look like this. With the, oh, that one doesn't have roll. Never mind, the previous version did. Again, we could get as complex as we want with, again, possibly having some genes more likely to mutate than others, or maybe giving it a higher chance of going up or down, maybe even by multiple points if it were very low or very high to begin with. And that would simulate the real-world phenomenon of regression to the mean. And lots of other complications we could add. If we run this on our new population, we might wind up with something like this, where green means it went up and red means it went down. Looking at the values in each column, you can see that it's now much more diverse. So now we assess how fit these newly created and mutated characters are. And again, sorting on fitness descending to make it easy to find the best, we get this. Now we can see for sure that this generation is much improved from the prior one. The old one went from 476 to 760, and this new one is from 635 to 851. It's still nowhere near our stopping criterion of 1,021, though. So fast forwarding through 6 more rounds, I eventually got this. One suitable character with 18 strength and constitution. Acceptable but subpar dexterity. Surprisingly high intelligence and shockingly low wisdom. If we really wanted it more specialized, we could complicate the fitness function further and do things like explicitly demand that it be well above average in all the class's important stats and forbid it to be above average at least well above average, in the other stats, or at least apply some kind of penalty. We could also modify either the fitness function or the mutation function to prevent the wisdom or any other stat from being quite so low. So now we've evolved a set of fighter stats. So let's suppose now our party needs a wizard. All we have to do is tweak the fitness function like so, to prioritize intelligence first, then wisdom and dexterity, and so on down to strength. Evolving it would follow the same process I showed earlier, so I'll spare you most of that, but after 11 rounds, I got a generation with 3 candidates 90% fit to be wizards. They're mostly pretty good in the other stats, but not so good as to be obviously better suited for some other class, except that top one looks like a decent bard to me. Now, suppose we want to evolve yet another kind of thing. By the rule of 3, it's now time that we extract the common parts into something that all the rest can actually use, with a name like, oh, say, Evolver. That's my actual license plate, by the way. With just a little bit of tweaking and a sprinkling of magic ruby dust, we can extract a class that defines the common parts and accepts another class that supplies the parts that vary. That's, I'm taking a picture, I'll pause a moment. There you go, okay. And this new class would run evolution on that other class like so. Now, I don't expect you to read that. We're going to go through it piece by piece. Since it's meant to accept another class and hold on to it for later, we can just use a constructor that does so. And just for fun, another parameter to define our population size. How to tell it to run evolution could look like this. Just a very slight variation on our original high-level code. Mainly, we're passing the responsibility for checking whether we're done, selecting the breeders, and mutating each candidate over to the class that got passed in. Creating the initial population could look like this. Nearly identical to our original code, but again, passing the responsibility for creating the new ones along to the passed-in class. Breeding a new population could look like this. Again, nearly identical, but passing the responsibility for exactly how that works over to the passed-in class. With this Evolver class supplying most of the infrastructure, we don't need most of the boilerplate that we had in the truckload and character classes. We can demonstrate that by evolving something else, and by using this and supplying only the parts that vary. So, what now? In my spare time, I make mead, a wine-like drink made by fermenting honey. Let's see if we can evolve a good recipe. Our recipes will be based on 2 simple factors: the ratio of honey to water and the alcohol tolerance of the yeast that we'll use. The resulting percent alcohol by volume, or ABV, and the sweetness will be how we'll evaluate our recipes. So I'm going to skip over how we get from those inputs to those outputs. If you really want to know, catch me some other time after I get this window back functioning again. There we go. And I can talk your ear off about making mead. Beyond simple creation, we'll need a way to evaluate their fitness. And this one looks at how far off we are from some desired target values, doing a bit of fancy math to keep them both close rather than just trading them off directly, one for the other. And you can see here we're targeting 12% alcohol by volume out of a range of about 0 to 20, and 15 points of sweetness, which is on a custom scale, which is, again, beyond the scope of this talk, but I can explain it later if you want. So this means that we're going for roughly typical wine-like strength and semi-sweet. We'll stick with the breeder selection function of just taking the top 2 most fit, but we'll need a way to combine them. which could look like this, sticking with the tactic of flipping a coin for each gene. And we'll need a way to mutate it, like this. And what this does is basically let it go up to 19% either up or down, but clamped within a reasonable range. Everything else is handled by the evolver class, and to use them together would look as simple as this, optionally passing how big a population you wanted to use. To demonstrate briefly how it might evolve mead recipes, an initial population might look like this, showing that it is possible to have negative fitness. It's just the ordering that really matters. And the next generation might look like this, with a slightly improved fitness and over a narrower range. And after just 7 generations, I got this, with one candidate a little weaker and sweeter than I wanted, but within our 90% fit criteria. If we get really picky and demand a 99.9% fit, going from 1.9 to 3, my first run like that took 45 generations to yield this, just a tiny bit weaker and sweeter than I wanted. And just like with the D&D characters, if we want something different, all we have to do is tweak the fitness function. So I asked for 7% alcohol and 5 points of sweetness, a low alcohol dry mead, sometimes called a session mead. And still demanding a 99.9% fit, it took 37 generations to get this, spot on in sweetness and just a tiny bit weaker. Then I asked for 16% alcohol and a sweetness of 35, a very sweet, strong mead, historically called a sack mead or great mead, very popular in Poland. It took 149 generations, but that was still very fast because our population is small and our criteria are fairly simple, to produce this, just a tiny bit stronger and drier than I wanted. There are lots and lots of other ways we can use genetic algorithms. They can create images and music and even code. I don't think that's going to replace us anytime, so don't worry about that. So think about it, and you might be able to come up with a solution to some problem that's been bugging you if you can use a genetic algorithm. And to recap what you've learned here today, genetic algorithms are optimization heuristics, which is fancy talk for a shortcut to find a good enough solution. They're simpler than you probably thought and can use very simple functions, but it can be tricky to figure out exactly what those functions should do. They're applicable to a wide variety of problems, including ones so complex that we mere humans would never think of some of the solutions that they can come up with. Now, if you have any questions, I'll take them either now or at the contact info up there. And as for the other URLs, that first one is for the GitHub repo, which has the code and the slides in HTML, because I'm using Reveal.js. It's also the CSS and images and so on. And the other one is for the slides as a PDF, much easier to consume, complete with a full script, which I've mostly stuck to. So, any questions? Yes, everyone back there.
The previous slide, you showed that if you want to use this, you also need to think very well about the rules, figure out the good rules for, I think, for assessing if you have the right data, right? That was that you showed that. My question is, couldn't you put that in the
Sorry, I'm having a little trouble hearing you from that far back. I think this might contain a microphone. Can you pass that back there?
Hello? Hello?
Next candidate for the rugged
I'm not sure.
team.
Yeah.
There we go.
So I'll try again. The second to last sentence can be tricky to figure out good rules. This might be a little bit out of the box, but couldn't you actually use the genetic algorithm to figure out the good rules as well? So basically, recursive algorithm. I'm not sure if this is actually possible at all.
Well, it's an interesting concept. I suppose you could use a genetic algorithm to evolve the code that you would then use in
Exactly.
a fitness function.
Yeah.
For that. So you would have to come up with a fitness function for that code, and maybe you can use a genetic algorithm to evolve that one. It's genetic algorithms, genetic algorithms, genetic algorithms all the way down. But yes, to your point, that is possibly, well, depending on your application, it could be simple enough code that you could use a genetic algorithm to evolve it.
Thank you.
Though coming up with a fitness function for something as complex as non-trivial code, that can be rather difficult.
Thank you.
Okay, you're welcome. Next question. All right, looks like we don't have a next question, so you get about 10 minutes back. 14.